Good day everyone! Welcome to the Liceo Math Club video tutorial. For this discussion, we will know how to determine whether a function is continuous on an interval or not. Much of a limit analysis relates to a concept known as continuity. A function is said to be continuous on an interval when the function is defined at every point on that interval and undergoes no interruptions, jumps, or breaks. If some function f of x satisfies this criteria from x is equals to a to x is equals to b. For example, we say that f of x is continuous on the interval of points a and b. The brackets mean that the interval is closed, that it includes the endpoints a and b. In other words, that the interval is defined as x is greater than or equal to a but less than or equal to b. An open interval a and b, on the other hand, would not include endpoints a and b and would be defined as x is less than b but greater than a. For an example of continuity, f of x for the first plot is x squared, such as x is greater than or equal to 0 but less than or equal to 1. For the second plot is negative x plus 2, such as x is greater than 1 but less than or equal to 2. For the third plot is x squared minus 3x plus 2, such as x is greater than 2 but less than or equal to 3. For the first point is y is equals to 0 and x is equals to 0. For the second point is x is equals to 3 and y is equals to 2. It shows that the minimum value of x is 0 and the maximum value of x is 3. For the y, the minimum value of y is 0 and the maximum value of y is 2. The function of f of x in the graph is known as a piecewise function or one that has multiple, pieces. As you can see, the function travels from x is equals to 0 to x is equals to 3 without interruption. And since the two endpoints are close, designated by the field in black circles, f of x is continuous on the closed interval 0 and 3. To think of it another way, if you can trace a function on an interval without picking up your pen and without running over any holes, the function is continuous on that interval. One of the more important theorems relating to continuous functions is the intermediate value theorem, which states that if a function f is continuous on a closed interval a and b, and k is any number between f of a and f of b, then there must exist at least one number c such that f of c is equals to k. In other words, if k is continuous on a and b, it must pass through every y value bounded by f of a and f of b. In the continuous function graphed above, for example, f of 0 is equals to 0 and f of 3 is equals to 2, so f of x must pass through all y values bounded by, and including 0 and 2 on the interval 0 and 3, which as one can see it does. Look at this example now of a function that is not continuous on the interval for which it is shown. F of x for the first plot is 2x, such as x is greater than or equal to 0 but less than 1. For the second plot, f of x is equals to 3, such as x is equals to 1. For the third plot is negative x plus 3, such as x is greater than 1 but less than or equal to 2. For the fourth plot is negative x minus 3 squared plus 2, such as x is greater than 2 but less than or equal to 3. For the first point, it shows that x is equals to 0 and y is equals to 0. Second points are 1 and 2. For the third points are 1 and 3. For the fourth points are 2 and 1. For the fifth points are 2 and 3. For the sixth points are 3 and 2. And it shows that the minimum value of x is 0 and the maximum value of x is 3. For the minimum value of y is 0 and for the maximum value of y is 3. The function shown in the graph is not continuous on the closed interval 0 and 3, since it has discontinuities at both x is equals to 1 and x is equals to 2. A discontinuity is any x value at which a function has an interruption, break, or jump, something that would require you to pick up your pen if you were tracing the function. The filled in black circles again indicate that the interval includes that point, while the open circles indicate that the interval excludes that point. The dashed line at x is equals to 1 shows that f of 1 is equals to 3, not 2. Since the above graph has at least one discontinuity, it does not satisfy the requirements of the intermediate value theorem, and therefore does not have to pass through every y value between f of 0 and f of 3. Even though f of 1 is equals to 3, however, the limit of f of x as x approaches 1 does not equal 3, since the function approaches a value of 2 from both sides of x is equals to 1. But what about the limit of f of x as x approaches 2? The function does not approach one specific value from either side of x is equals to 2, but we can still describe its behavior from right or the left. This is the basis of one-sided limits, which is the topic of the next section. Let us determine if this example is continuous on the closed intervals or not. The f of x for the first plot is x plus 1 raised to the power of 2 minus 1, such as x is greater than or equal to negative 2 but less than 0. For the second plot, 5 over 4 multiplied to sine multiplied to pi minus x over 2, such as x is greater than or equal to 0 but less than 2. For the third plot, x minus 3 raised to the power of 2 minus 1, such as x is greater than or equal to 2 but less than or equal to 4. For the first point, it shows that negative 2 is equals to x and 0 is equals to y. For the second point, x is equals to 4 and y is equals to 0. The function is continuous on the closed interval, which is negative 2 and 4, for which it is shown. So this concludes our topic for this week, and I hope that you've learned something. Thank you. Stay tuned for more tutorial videos.